We will start this lecture on basic designs. So this is part of the course on experimental design for research animals, and these are the different kind of designs that we will see. So we will have the two most commons, that are the completely randomized design and randomized complete block design. And then we will see factorials and non-orthogonal designs, and even regression ones, and covariates and contrast and least squares. So we will split this into different blocks. Okay, so the objective of this lecture is to learn that a tool that is much more powerful than the typical student t-test with a couple of groups. So let's see how we can do it. So actually we will start with a couple of groups, and this data could be analyzed with the student t-test, but we will use a different tool that is more in the direction of Anova and linear models. So let's say that we are testing a new drug at a given concentration, at a given dose, that we are studying whether it lowers the blood pressure of hypertense people. So we will have 1000 hypertense people, and we will give half of them the drug, the other half will receive the placebo, and we will divide the 1000 people in two groups, and for each person each person will be randomly assigned to the treatment or to the placebo. And then we will have for each person we will have a blood pressure measurement. So we will have, in the first group, we will have person 1, person 2, person 500. The Y is the blood pressure of that person, and then in the second group we will have the same. So second group, first person, second group, second person. So in this notation, the first subindex is the group, the second one is the person. So we can compute the mean of the groups, so that is the mean over the second index. So meaning that we don't care which person you are, but we compute what is the mean of that group, and we do it for group 1 and for group 2. And we will, when we average over a subindex, we will put a dot, just to say I don't care about that index, that specific person. And then we can compute the overall mean of the 1000 numbers, and then we are also averaging the first index. So we are averaging, we don't care about the specific person, and we don't care about the specific group. So this will be the overall mean. So the model of linear models assume that the data are generated in this way. So the observation, the blood pressure that we get for a person in group J, and this is the kth person in that group, will be an overall mean plus something that depends on the treatment, that he has received or she has received. So the placebo or the placebo or the drug, plus something that I cannot explain, that is the residual, and that residual is specific for that person. That is why it has a couple of indexes. And there's a constraint in linear models that is that the sum of all the treatments, they have to be 0. So we can compute different averages. So we can compute the overall average. So we have to sum overall J and K, and we have to divide by the total number of individuals. And this overall mean should be close to should be an estimate of the overall mean. So this is the population mean, this is the sample mean. And then the average of the observations in one of the groups, it is the same. We simply have to sum overall persons in that group, and then we divide by the number of people in that group. So, and this should be an estimate of this part. So if you average over the k, this part doesn't depend on k, but this one does, and we are averaging over people, and these residuals, they are supposed to have zero average. Okay, so why this constraint? Or well, let us have a graphical representation of what we're doing. So let's say that you have the two groups, the control and treatment, and each one of these dots is one of the people in those groups. So we will have an overall mean that should be mu, that is more or less here in the middle, and then we have the mean of the two groups. So the mean in the control group, and we don't care the person, and they should be the overall mean plus this extra that goes from the overall mean to the mean of the group. This is the effect of the treatment. And then for the other group we have the same. We have the overall mean plus this extra, but this extra now is negative, but still we have to sum, but we have to sum a negative number. And this is a positive extra, this is a negative extra, and they need to be exactly equal to each other, because the sum of the two has to be 0. And this constraint here is to make the model unique. Otherwise, there could be many other decompositions, and we don't want all these alternative decompositions. We just want one of them, that is this one. This is the one that Anova uses, and it has to be understood in a proper way. So let's say, let's put some numbers. So let's say that hypertense people, they have a mean in the control of 16 millimeters of, so it is 16, and then when you give the drug, then it lowers to 14, let's say. So the overall mean is 15, and this 15 has an extra positive value if you are in the control, because you haven't received anything, and then you are at 16, but then a -1 if you are in the treatment group. So it doesn't mean that being in the control rises your blood pressure. It is that you have your blood pressure. All these hypertense people, they have a blood pressure about 16, but if you receive the drug, then it lowers it by 2 units. So that is why the treatment is lower. The mean of the treatment is lower, because you have lowered 2 units because of the drug, but then the overall mean has shifted down, and it seems as if the control rises the blood pressure. Okay, so when we are using Anova, what we have to compare is that this difference between the control and the treatment group, that is 2 units, we have to show that it is much larger than the noise. And the noise is the variability between the people within a group, and the same here. And by the way, Anova assumes that the variability in all groups is the same, so the variance here is the same as the variance there. Okay, so let's see how this is done. So what is the variance? The variance is or the total variation. So the variance is divided by the number of samples, and the number of samples minus 1. But so the total variation is, you take every person, so this person 1 in the control group, and then you compute what is the distance between this person and the overall mean. So we have it here, and you would do the same for all the other people in the treatment group. So you measure from this point to the overall mean. This is the total variation of the numbers that you have seen, and then you hope that this total variation can be explained by 2 things. One is the difference between the control and the treatment group, that may be significant or not, And the other one is something that you are not able to explain, and that we will call residuals or noise. So when we go from this person to the overall mean, we can do it in 2 steps. So the first step is from that person to the mean of the group. This is the noise, this is the variability of within this group. And then we can do a second step that is from the mean of the group to the overall mean. So if there are no differences between control and treatment, then these 2 lines will be very close to the overall mean, and then there will not be any difference. So it can be shown, and we have it in the next slide. It can be shown that this total variation can be decomposed in various sums. So the first sum is the sum of all treatments. So each person is contributing with this second step, simply because it is in this group or this group. So it is every person, every J, is contributing with the effect of its group, of his group or her group. And then the other part is the contribution, the difference between that person and his own group. So in general, what we see here is the total variation that we see in the numbers is a function of how different the control and treatment groups are, and how different the people are from their own group means. Okay, so here is a reasoning about the total sum of variation. It is simply just to see how we can put this thing as a function of multiple elements that we have in there in the problem. This capital sum is the sum over j and k, and that is why it has dot dot. And yeah, but you don't have to pay attention to this. This is just if you are interested in this kind of things. And then how do we estimate the treatment, the effects of each one of the groups? So one simple way, and this is only valid if you have balanced results, so or balanced designs in which you have the same amount of people in both groups, in the placebo and the drug, then you can compute the mean of the group minus the overall mean. This is what is somehow implied here. So you have the mean of the group minus the overall mean should be the estimate of the contribution of the group. Okay, so this is here, and the associated variance is this one. Okay, so yes, it is just this term, and so this is the part of the sum of so we have the total variability that we haven't used any subindex. We have the sum of the treatment, and we can do the same for the residual. So an estimate of the residual of a person is the value of that person minus the mean of the group, and this is an estimate of the residual of that person, and we can compute the sum of the squares of all the residuals, and it is this thing. And then you can show that this one plus this one is equal to this one. Okay, but it has a very simple intuition. So the sum of squares can be decomposed in 2 parts. One that is coming from the treatments, another one that is coming from the residual. So here is the sum of squares is the total variation. So it is the difference between each person and the overall mean. And here we have the sum of the treatments, that is the difference between that person, between the group of that person and the overall mean, and the residuals, that is that person and the mean of its group. And we can make a similar decomposition of the number of degrees of freedom. So degrees of freedom has to do with the rank of some matrices that are involved in the analysis, but intuitively speaking, they are kind of coins. So every time that you make a measurement, you you get a coin. So if you have done 1000 measurements, you have 1000 coins. But then you have to spend these coins in estimating parameters. You have to estimate the overall mean. So you have to spend one coin for that. Then you have to estimate the mean of each one of the groups. So this TJ, so these extras that you have for each one of the groups, and then you would have to spend 2 coins here. Actually, you can save 1 because you know that they have to be, the sum of all of them has to be 0. So once you have 1, the other one comes for free. And if you have, in general, if you have T treatments, T minus 1 coins you have to spend in estimating the parameters, but then the last one is free because the sum of all the treatments has to be 0. So yeah, this is what it is said here. So you have 1000 coins. So 1000 coins, you have 999 degrees of freedom because you have to spend 1 in the overall mean, and then you have to spend T minus 1 in the treatments, in the groups in the extras of each one of the groups, and then for every person you have to estimate also what is the residual. So all those that you also have to spend coins. So and it is the rest of coins. So we will see them this in the next table. So I think it is more clear here. We will come back to the previous one. So you had 999 degrees of freedom in total. You have spent 1 in estimating the treatments because the second one comes for free, and then the remaining 998 you have to spend in estimating the parameters of the residuals. Okay, so you arrange all this information in a table. So you will have a table in which you have the total sum of squares, the total number of degrees of freedom, and then you will annotate how many degrees of freedom you have spent in the treatments, how many are left for the residuals, and what are the sum of squares of the treatments and the residuals. So these things we have seen. And then we will compute something called the mean squares. That is, these sums divided by the number of degrees of freedom that you have. So it is how much variability, how much sum of squares each one of these parameters is explaining. So you divide the two, and you will have these mean squares for the treatments, mean squares for the residuals. And when you want to show that the treatments are effective, what you have to do is to compare the mean squares of the treatment to the mean squares of the residuals. And that is a statistic called F that follows an F-Snedeker distribution, and the F-Snedeker distribution has 2 parameters that are the number of degrees of freedom with which you have calculated. So these 2 numbers of degrees of freedom. Okay, so I think it is more obvious here. So this is the sum of squares for the experiment of the placebo and the drug, in which we had 500 people in each one of the groups. So we had 1000 measurements, 999 degrees of freedom in total, and 1 for the treatment. We have spent 1 in the treatment. We have spent 998 for the residuals. And then we compute the mean squares. So the mean squares is the ratio between these two. So that means that each one of these degrees of freedom is buying a variability of 256, while this one is 13.61. So that means that so this F, that is the ratio between the two, is a signal to noise ratio. It is how much signal do you have, how much evidence do you have in favor of your treatments when you compare it to noise. So if the treatments are very effective, the variability explained by the treatments should be much larger than the variability explained by each one of the parameters from the noise, and this is the case. So it is 18, almost 19 times more variability is explained by the treatments than by the noise. And this has the compositions that we have seen here. So the total sum of squares is the sum of squares of the treatment plus the sum of squares of the residuals, and the same for the number of degrees of freedom. They are explained here. So the total sum of squares is the sum of the two contributions, one coming from the treatments, another one coming from the noise, and the same for the degrees of freedom. So the total number of degrees of freedom is some of them are spent in the treatments and some of others are spent on the residuals. And then we have to take a decision. Are the treatments effective? And then we will make a test, and the test is the Anova test is that the mean, there is no difference between the mean of the different groups. So we have two groups here, so there is no difference between them, and if this null hypothesis is true, then this F is distributed as an FF-Snedeker with 1 and 998 degrees of freedom, that are the ones that we have used to construct this table. And then in this distribution we will look for the percentile of 95%. If that is 3.8. If our F, the one that we have observed, is larger than this critical value, we would reject the null hypothesis, and we can calculate the p-value as the area of this distribution from this point to infinity. Okay, so we see that our groups are really, our treatments are really effective. Okay, we may now complicate a bit more this design. So we may know that some of the variability is caused by some other factors. So let's say that we think, we are not sure yet, but we think that sex and age may have an impact on blood pressure. That probably has. And then what you would do is to construct blocks that are as uniform as possible with respect to the variables that you think that will have an impact. So if you think that sex and age will have an impact, then you would divide all samples into males and females, and then males into young and old, and females the same. And then once you are here, you have a homogeneous group. So you have only young males, old males, young females, and old females. And then within these groups, you assign randomly to each one of the groups. So what we did before, we had all the people, and then with disregarding their sex and their age, we were randomly assigning to each one of the groups. Now it is not disregarding sex and age, but we make homogeneous groups of sex and age, and then within that homogeneous group we are randomizing. So the name block comes from agriculture, because all these things study experimental design studied in agricultural studies, and then what they wanted to have there is homogeneous groups of homogeneous regions of land, and so that is within that region they have uniform soil, uniform drainage, sunlight, or other physical characteristics. But for us it is the same, so we want to have homogeneous groups with respect to the variables that we think that may have an impact. And here is another example. So let's say that you're doing an experiment and you think that the age may make a difference whether you have diabetes or not may have a difference. And then this is a multicentric study, and then the center itself can make a difference. So part of the variability is caused by the center and the diabetes and the age. So once you have homogeneous groups with respect to the center, diabetes and age, then it is where you randomize. So within each center you randomize into control and treatment groups. And now that the composition is a bit different, not too different. So what you are saying is that the blood pressure, so let's say that we make only blood pressure and we study only one block, that is male female. So you are in block I, so block I is male or female, and TJ is the treatment that you have received, so either the control, the placebo or the drug, and then something that depends on the person. So the blood pressure that you measure for a person that is in block I, treatment J, and that is the person K, is decomposed as this. So an overall mean plus something that depends on your block plus something that depends on your treatment plus some noise. And as we did before, we constrain the blocks to have zero sum, and also the treatments to have zero sum. And then here is how you can estimate all those parameters. So for instance, the overall mean would be the mean of all observations. The contribution of the blocks is the difference between the mean of all people within that block and the overall mean. So for instance, what is the contribution of males? So you compute the mean of all males independently of whether they have received the placebo or the treatment, and then you subtract the overall mean, and then the same for the treatment. So you compute the average of all people receiving the placebo disregarding their sex, and then you subtract from the overall mean. So these are ways to estimate the block, the treatment, and what about the contribution of a person? So I think this one is the easiest one to see. So it is you have the observation for that person, and then you have to subtract everything that you have already explained. So I have explained the overall mean, I have explained the block, I have explained the treatment. So whatever is left is what I cannot explain, and that is the noise. Okay, so you have the observation for that person minus your prediction that is based on the block and the treatment of that person. And then you can calculate again all kind of sums. So the overall sum of squares, the contribution of all blocks, that is, you recognize it is very easy, and the contribution of all treatments, the contribution of the residuals, and we have the same kind of decompositions equations that we had before. So the overall sum of the squares is a part of it is explained by the blocks, part of it by the treatments, and a part of it by residuals, and the same for the degrees of freedom. And you organize them again in the table, and when you compare, you have to compare always the treatments to the residuals. So the variability explained by the blocks will be taken out from this comparison. So here is the same example that we had before. The total sum of squares has not changed, and the total sum of the treatments has not changed either. The degrees of freedom that we had are the same, but now we have a new actor, that is these blocks. So these blocks explain 1500 of the sum of squares. So there are differences between males and females, and this variability is taken away from the residuals. It was some part of the variability that I could not explain before, but now I can explain because I have measured the male-female status of each person. So part of the variability that I could not explain before, now I can explain, and I can explain with only one parameter. So actually the regarding blood pressure, sex explains much more than the treatment itself. So it is like 6 times more. The blocks explain 6 times more than the treatments, and to show that the treatments are significant, we have to compare the treatments to the residuals, to the part that you have not been able to explain. There is no free lunch because you have explained a lot through the blocks, but you have spent 1 degree of freedom. But this is very cheap. You had 998. You don't mind spending 1 in the blocks. And now you may remember before each parameter of the residual was explained in 13.61 and the ratio was 18.87. Now instead of 13 it is explained in 12, and now when I compare these two, the ratio is not 18 or almost 19, but it is 21. So it is even much more explanatory than noise. So the distribution has changed a bit because now this is 99.7, not 8, and but yeah, still the p-value is even better than what I had before. So by introducing the blocks, what I have gained is that I can now explain a lot of variants if it is true that the sex and the age or any other block explains part of the variability. You will be able to explain that part of the variability with very few degrees of freedom, and if they don't explain anything, doesn't matter, so this will not be significant, but it has taken out part of the variability from the residuals. So if the treatments are significant or not, now it will be much easier to show, and this gives another interesting second thought, that is, if I want to try my drug with in males and females, I don't have to double the size of the experiment. So I don't need to do it with 1,000 males and then 1,000 females. Estimating the contribution of male or female, it takes only 1 degree of freedom. So with only 1 measure more, I have the same power as before. And if there is really a difference, then I will be able to see it with only 1 more measure. So I don't need 2,000 people to do the experiment, but I need 1,001. I can make 1,002 because I want both groups to be balanced. And here we introduce another interesting idea, that is, let's say that you are looking for what is the optimal spacing between plants, and you want to see what is the yield of those plants, and you think that you will apply 10 treatments. So this is the separation in X and Y of the different plants, so 30 centimeters, 30 24, so there are multiple combinations. And to avoid possible land effects, we will divide the land into 4 blocks, and within each one of the blocks we will apply the 10 treatments. But those are quite a lot of tests. So at some point, when you say, okay, not all the means are the same, so you have to see which pairs are different. So you are making actually quite many comparisons. So you are doing all possible treatments versus all the others. So that is 10 times 9 divided by 2, so 45 different comparisons. Anova is prepared for that, so there is not a multiple testing inflation error if you do it carefully. But actually you have spent 9 degrees of freedom in estimating the parameters of the treatment, when in fact all these treatments are variations of how much area you have each plant is having. So for instance here the 30 times 30, each plant is having an area of 900 centimeters squared, and then what we can do is a regression analysis. So instead of putting this model in which each treatment is receiving, we have to estimate what is the contribution of each one of the treatments. We will see later around this lecture that we could have done differently. We could have just with one parameter we could have estimated what is the effect of the treatment, and there is an extra advantage, that is we will be able to predict the values within in locations that we have not explored. For instance, we have not explored 30 times 28, but we will be able to predict it because of the regression. And if there are clear variables to block, you should block them, and these ones are litters. Typically they're chosen as blocks because all the pups from the same litter, they are somehow related. So the litter in total may make a difference, and you wanted to use it as block. So half of the pups would be given to control, the other half would be given to the treatment. And then you may use also birth weight as a covariate. We haven't introduced covariates yet, but the birth weight can also make a difference, and part of it can be explained by this factor. And if there are no obvious blocking variables, you may create still blocks as insurance. So for instance, you can create patterns within the shelves, or you can so maybe these upper rows in the shelf, they are closer to the light, and then these ones are farther away from the light, and then the response of the animals are different, or they're I don't know, the room in the animal house may make a difference, the person doing the experiment. So you can create blocks for multiple reasons. And at the end, your experiment should look like this. So remind that we were saying in the first lecture that you always have to randomize. So your designs should look like homogeneous blocks. So for instance, here it was an experiment in which we were studying the effect of a couple of 3 treatments, and each treatment could be given with an adjuvant or not. And then these treatments are applied on homogeneous blocks. So you have 2 kinds of tumors, and then you have sex and age. So you would have an homogeneous group that is all females with tumor 1, and then within these they are randomly allocated to the treatment, and the same for each one of the blocks. And you may observe an interesting feature here, that is the combination of treatments does not need to be the same in each one of the blocks, and the block sizes do not need to be the same. So you see there are bigger blocks like this one and a smaller block like this one. I have cut the experiment, so it continues here with male old tumor 2, male young tumor 2, male young tumor 1, tumor 2. So not all the blocks need to have the same size, and not all the blocks should have a balanced application of treatments. So you see here treatment B is applied 4 times and treatment C only once, but here P is twice, C is twice. So this allocation is random. So it is better if you have balanced designs. Balanced is that all blocks have the same size and they all see the same amount of treatments, but it is not a compulsory constraint. So you are not restricted to that. If you have them, it is better because you can the comparisons, there are some comparisons that are, and the variability of those comparisons is affected by the composition of the treatments within blocks, but it is not compulsory that they are homogeneous. There are some other constraints that we will see along the course, and intuitively what we can say is that it is ideal if all treatments are applied in all blocks. So if in this block we only apply treatment A, it would be a problem because we cannot compute what is the effect of treatment B and treatment C. So this would be all for the completely randomized design and the randomized complete block designs, and I hope you have got the idea that with these it is much better than the T-student, especially the ones with blocks. So with the one of blocks, you can explain part of the variability as part of the blocks, and then you are free to compare the treatments to the residuals. But this comparison is much more significant because part of the variability you have already explained through some other means. And the other advantage is this one, that you can include multiple treatments in the comparison that with the student t-test you can not. So you would have to do pairwise comparisons to the control, and then you're having this type 1 error inflation, that is having a probability of false positive that is larger than what you think. So this would be all for this section, and see you in the next one.